So good morning. I'm very honored to start our wonderful day. And I want to start by acknowledging that while I really hope that you'll find my talk memorable, let's face it, most of the things we hear in life, we forget. And nevertheless, there are these instances in our life that we hear something that is so groundbreaking, so shocking, that not only we remember it, we also remember exactly where we were and when we heard it. And such an instance for me was the day I heard there is finally a cure for cancer. It happened in 2007. I heard a fascinating talk by an American scientist that said that in his institute, they found a way to finally crack the cancer manual. So they found a way to sequence and read the genome of each and every cancer cell. And by that, they could see what is wrong with the cell and fit the right therapy. And he said that while this is now happening only in academia, in a couple years from now, all around the world will be able to read the manual of each and every cancer cell and fit the perfect drug to kill it. This was more than 16 years ago, and I'm standing here in front of you today in 2023, and there are still people who are dying of cancer. So what went wrong? Why haven't we cured cancer yet? So the first thing to acknowledge, and it is very important, is that this revolution, the ability to read the cancer manual, had had tremendous impact on patients' life. Patient outcome today is far better than it was 20, 30, 50 years ago. There are people living today with cancers that 10, 20 years ago were considered a death sentence. So more patients are surviving cancer than ever before. And if we look at the numbers, 2 in every 3 patients would reach the 5-year survival mark. But in this terminology also lies our biggest problem, because we don't measure success by curing cancer. We're measuring success by being able to reach this 5-year mark. And the reason we're using this number is that too often we see that cancer eventually comes back, sometimes months, years, even decade after a successful initial therapy. So if we're so good at curing cancer, at killing cancer, why does it come back? And what has emerged as one of the reasons is this concept of cancer persister cells. So what are cancer persister cells? These are cells that don't follow the manual. If you look at their genome, if you look at the cancer manual, they should have died when we gave the drug. Unfortunately, these cells do not follow the manual. And despite having no alteration, no genetic mutation that should confer resistance, they still survive therapy. So my lab is devoted to studying cancer persister cells to understand what enables these rare cells to survive therapy, despite the fact that they should have not. And how do we start studying something that we don't understand? So what we do is we do something very basic. We just look at it and see what is happening. So what you see here is each and every dot here, each and every circle is a real cancer cell taken from a patient. And we can label these cells green and image them, treat them the same way we treat patients in the clinic and see how they respond. So I'm now going to show you an image of these cells as we treat them with the same drugs that are given to the patients in the clinic. And you can see that at the beginning, they proliferate. But then at later days, so here you see the days, most cells die, and we have rare cells that can not only survive the therapy, again, they have nothing in their manual that enables them to survive, but they can also expand and grow and create this big cell mass. So we took these cells and we said, what is special about these cells? How come they can not only survive, but also proliferate and expand despite the fact they should have died? And what we found is that these cells have the ability to switch their diet. If most cancer cells prefer to consume glucose, and there is a Nobel Prize in 1931 on this effect, our cancer persister cells prefer fats. And this special dietary switch now gives them the ability to survive therapy. And what we saw was that if we prevent these cells from consuming fats by adding a drug that is not toxic, we can not only kill the cells, we can also prevent the cells from proliferating. So if before we got more cells, now we get less persister cells, and the cells that do survive are less aggressive. Now this made us very optimistic, because here are the cells that we were told, we thought, that cannot be killed, and clearly there are ways to kill them. There is a way to prevent their growth. So starting with this, building upon this, we are trying to now uncover what is the manual, how do these cells survive therapy? And to do so, we are looking at a wide range of different traits that we can measure, including what molecules like protein and RNAs are in these cells. How are these molecules organized? Maybe the code is not different, but the ways that the pages are set is different, and this enables them to survive. And lastly, also looking at their metabolism. And think about that. There might be very easy intervention that we can give to try to prevent these cells from recurring. And I just want to acknowledge that being able to decipher this manual is not something that is going to happen overnight. There are many, many people around the world, including members of my lab and members of other labs, that are working hard in order to try to really understand what is happening in each and every cell so we can target it. And they're working hard because they're all united by one single dream. And it is that one day you will be able to tell your grandkids that you remember exactly where you were the day you heard that cancer was finally, ultimately cured. Thank you.
Questions?
So you were talking about cancer very homogeneously. So I don't know, is everything you said applies to every type of cancer, or is this a specific type, or?
Yeah, so that's an important question, right? Are persister found in all cancer types? So there are very few cancer types where we know that we can treat and get with treatment complete cell killing. The assumption is today that in the vast majority of cancers, there are residual cells that are left after treatment. And the difference from the patient perspective is if they will regrow or not. But the overall, I would say, assumption here is that in the I would want to say more than 90% of cancers, there are residual cells that are left. And that some of these cells do not have any genetic resistance that can explain it. I would say, just to give a sense, that what percent, of course, changes from one cancer to the other. If we're talking about lung cancer, for instance, 40% of the patients that recur don't have a known genetic mutation. This changes, of course, in other cancer types, but it seems to be very, very, very prevalent.
Great talk, Yaara. Thank you. I'm curious about these cancer persister cells. Do they express certain markers that are shared between patients, or defined only by the fact that they survive the treatment?
Right, so that's an important question about what are the features that characterize persister cells, and also thinking from the translational perspective, if there are markers, maybe we can try to find them and fit a drug. So there isn't, I think, a consensus. The jury is still out how similar are persister cells and if there are certain markers. I would say that there are big efforts now. There is a big effort, €14 million effort in Europe now that is called PersistSeq, to go and try to answer your question. They're sequencing in different methods, RNA-seq and so on, looking at different tumors, and they're trying persister cells, and they're trying to see if there is some commonality. But I just want to maybe take this question to explain that it's very hard to ask a patient that is feeling well to come into the clinic and give a biopsy, right? These are patients who are undergoing remission. There are very few cancer cells in their body. They're feeling well. So it's also, I think there is also this understanding now that if we want to be able to target them, we need to be able to answer your question. And for that, we need more patient samples. And there are big endeavors now, one in Europe and another in the US to try to collect these. And I'm very, and I think we should be very grateful for the patients who are coming into and giving biopsies when essentially they're feeling good, right?
Just introduce yourself.
So my name is Max from Tel Aviv University. I'm interested if you see acquisition of mutations after a while in your persister cells when you treat them. You said that at first they survive and they even proliferate for a couple of days, but do you see eventually a point mutation or a selection for genetic alteration that occurs later, not in the beginning but later?
Right. Yes. So this is, I think, kind of why should we care from a genetic perspective, or are there implications to being a persister? And I would say that there is, we have good evidence in vitro and in vivo that cancer persister cells are a reservoir for genetic mutations. We don't exactly know how that happens, if they're proliferating, so they have time to acquire mutation. We know that similar to bacteria, it was shown in colorectal and in lung cancer, that persister cells have elevated mutation rates, so they're more prone to acquiring a genetic mediating resistant. And I think one of the interesting kind of thoughts around that is that perhaps we can find drugs that can target evolvability of persister cells, and that is something that was done in bacteria. So cancer persister cell is a new field, but in bacteria they've been studied for more than 80 years. And we know that you could think of, there are drugs that in bacteria can affect evolvability, and then perhaps we can kind of buy time till we have the next genetic mutation. So that's a completely different, I think, novel therapeutic avenue that we have not tried in cancer yet.
Thanks for the great talk. My name is Sam. I'm from the Weizmann Institute. Do you think combining today's cancer treatment with, like, for example, metabolic inhibitors would represent like new perspectives in this regard? And what do you think regarding, like, for example, applying metabolic inhibitors? Wouldn't be the cancer stem cells be protected in their own niches because they normally have like different metabolic activities that are very different from the rest of the body? Like, what do you think?
Right. So I think this question about can we manipulate metabolism to maybe get better clinical outcomes, but also bearing in mind that might have an effect on the normal physiology is something that there is active interest in, right? Cancer and metabolism is a very hot field, and I think one of the reasons to go into that field is because there are many FDA-approved drugs that can target metabolism. And many of them can be taken for a long, long time without having severe side effects. So maybe we could give them to cancer patients and affect these metabolic aspects of persister cells. So it is a very young field, but I would say that one of the hallmark of persisters is activation of mitochondria, so this metabolic switch. And there are definitely more things that we can do to try to see if we can modulate it. Maybe, as you kind of suggested, there is also a way to systemically modulate it, but we need to understand how that interacts with cancer stem cells and model where there are cancer stem cells, as well as with the whole body physiology, right? But I think that it's a very exciting world to go into because we already have so many drugs, right, for metabolic syndromes that are less toxic than the drugs we're usually giving our patients.
Hey, Rafael from Bar-Ilan. I thought when you said about the switch of metabolism, I thought about the ketogenic diet that people are using. So I was wondering, like, before going into any drugs, any link between like a diet. I know the scale is very different from what we eat to the cells metabolism, but don't you think like we can be any possibility to develop diet to go along the process of curing cancer to push toward any of metabolism, which would be sensitive to treatment?
Yes, so I think, again, I think this question, so with ketogenic diet, is that there are already patients who are switching their diets, right? Because there is this, I don't know if you want to call it belief, there are different ways that people can treat cancer. And I think there is what we do, and there is also, people who are trying to do dietary intervention. And someone told me yesterday something nice. She's from Russia, and she said, when my grandmother told me, you have to eat this because otherwise you'll be sick, we laughed at her, and now there are like all these studies coming out, and my grandmother was right, like I should eat this soup, it's like good for me. So I think that, as you alluded, there is still somewhat of a distance between like seeing if the ketogenic diet, what exactly is happening, but I think there is reason to believe that there might be ways to do dietary intervention. I don't know specifically what and how to try to get less, again, better outcomes. I think on the more like wearing more my, scientist hat now, scrutinizing, we're all used to being very judgmental, is that I also want to be very careful when we go and tell people you should do this dietary intervention versus the other before we have good evidence. So I think it's definitely an exciting thing to try, and there are people who say that it works for them, but we really need to go back to our basic models and see if that has an effect. Yeah. But there are a lot of things to try. So I want you, I'm the first talk. I want to end on an optimistic note, right? We're all here. We're working towards one goal, and there are many good ideas also here to really improve what we're seeing today.
Thank you, Yaara. We will prevail.